Hello everyone, welcome to our lecture video where we're going to touch on chemistry just a little bit. Fair warning, there's not going to be a whole lot of pictures in this one. So why even learn about chemistry in anatomy and physiology? Why do we even study it? Why do we even look at the basics of it? So chemistry actually shows up in a lot of different forms in anatomy, mostly in physiology part of it. So you've heard of electrolytes, you've heard of different solutions, drugs, reactions, etc., etc. Well, we talk about and learn about chemistry to understand physiology. So remember, anatomy is form, what it does, anatomy is the form. It is what we're looking at. This is what this is. Well, physiology is the function. It is how it works. So to understand physiology, we have to have a grasp of basic chemistry, essentially. So some terms that most of us have been familiar with since elementary school, but we're going to touch on here. Matter, definition, that's any substance that has mass, that takes up space. It's a stuff that takes up space and has mass and weight, right? Simple. States. So think about states of matter: solids, liquids, gases, plasma. When we talk plasma and states of matter, we're not talking blood plasma. We're talking the sun. Blood plasma is actually a liquid. It just happens to share the same name. So fun fact, as far as anatomy goes, we'll only be talking in solids, liquids, and gases. Energy. Okay, we know what energy is. So we have energy being used all day. We're moving our muscles. Our guts are moving waste through. Our heart is pumping blood. All of that is kinetic energy. Energy in motion, energy in use. Kinetic anything means movement. Think kinesiology. Kinesiology is literally the study of human movement. So anytime you see kinetic, no, we're talking something in motion, right? Here we're talking kinetic energy, so energy in motion. Potential energy is stored energy that has the potential of being released, right? So potential energy, it can be released during a chemical reaction, but it's stored energy. It's just waiting on something to happen so it can release some energy. And we have several different storage forms of energy, several different types of potential energy in our body. One you may heard of in other science classes is ATP, adenosine triphosphate. So ATP is a stored form of chemical energy in our body. Glycogen is another example. Glycogen's in our muscles, it's in our liver. When we need energy, glycogen bonds break and eventually release 2 ATPs. Call that glycolysis. Cellular respiration, which you might remember from a different biology class, that one we use glucose and oxygen for even more ATP, about 34 to 36 ATP of potential energy being released. So once it's released, right, if something's moving, it changes to kinetic energy. So that's interesting. But glycolysis and cellular respiration are just examples of potential energy where it's stored. There are a bunch of other potential energies within the body. If energy is wasted and it's not used up, overall, any inefficient use of energy causes heat to be released. Luckily, our bodies are pretty efficient, so we don't burst into random flames. On the small scale, we can generate heat by shivering. We can generate heat by rubbing our hands together if we're cold. But overall, the body is a pretty effective user of energy, and not a whole lot of it gets wasted. Parts of matter. So you guys remember the periodic table of elements. If not, it should be in your textbook. And of course, you can always Google it to get an image of the entire table. But we're going to talk about the basics of periodic table of elements to understand isotopes. So what I really want you to gain from this slide is what isotopes are. But we're going to start at elements and work our way down to isotopes to understand them. So again, periodic table is made of elements. Each element has a chemical symbol. So that's the abbreviation for that element. So O for oxygen. And then, of course, oxygen is the element name. The atomic number is the number on top of the O, and then the atomic weight or the atomic mass is the number below the O, the oxygen, right there at the bottom, the 15.999. So yeah, that's basically what you're looking at there. So what is an atom? So an atom is the basic smallest unit of, is basically the smallest unit of an element. The only thing smaller than an atom are its subatomic particles that make up an atom. So those are our protons and neutrons, which are in the nucleus, and then our electrons. So the protons have a positive charge, electrons have a negative charge, neutrons have a neutral charge or no charge, 0. So if you know that protons are positive, neutrons are no charge, 0, neutral, then you know that electrons are negative. That's the only one that's left over. And again, like I said, to understand isotopes, we're going to talk about this a little bit more. So right now we're going to talk about math, atomic math. Not very difficult. The atomic number tells you the amount of protons that the element has. So oxygen has 8. And then the atomic weight or the atomic mass tells you the amount of protons and neutrons. So if there are 8 protons, how many neutrons are there? 7.9999, right? And that's what creates the mass and the nucleus of the atom. The protons and neutrons are in the nucleus of the atom, and the protons plus the neutrons equal the atomic mass. Where it gets a little complicated is when we do actually talk about isotopes, but we'll keep it pretty simple. We're not going to get into the nitty-gritty of it all. But isotopes are versions of the same element with the same number of protons, but a different number of neutrons. So having a different number of neutrons is going to change the atomic mass of an element, right? So if there's an extra neutron, instead of 15.999, it's going to be 16.999. So now we have a different form of oxygen, for example. But anyways, once we change the atomic mass of an element, now we have an isotope. So it's the same number of protons, but different neutrons. So the atomic mass is different from what it started at in that element. Now, not all isotopes are radioactive, but those that are radioactive we're able to use for medical purposes. So for the purpose of this class, we're only talking radioactive isotopes that are used in medicine. So specifically here, we're going to talk about treating cancer. So please know what an isotope is and how it's used. Iodine isotopes are used for thyroid cancer, iridium isotopes for breast cancer, palladium for prostate cancer, rhenium isotopes are used for bone pain or bone cancer, and then lead isotopes for pancreatic cancer, for ovarian cancer, and for melanoma, which is skin cancer. Solutions and suspensions are important in anatomy. To understand those, we have to rewind back to molecules. So molecules are 2 or more atoms of the same molecule combined. So 2 oxygens make O2. Compounds, however, they are 2 or more atoms of different elements combined. So if we have 2 hydrogens and 1 water to combine, now we have H2O. So that tells you water combined chemically, and water is a compound. Now, a mixture is when there are 2 or more substances mixed together, but not chemically bound, not chemically combined. Mixtures can be separated. Compounds and molecules cannot. Compounds and molecules, those bonds can be broken, but that's a whole nother topic you'll learn about in chemistry specifically. We're not going to get into the details of that. Mixtures, think more like salt and pepper. You can mix the two together, but you can also separate them apart. The salt is still going to be salt. The pepper is still going to be pepper, right? It might take a while, but you can. You can mix them. Or you can mix them. You can take them apart. You can mix them. You can separate them. The salt's still going to be salt. The pepper's still going to be pepper. In the body, we have mixtures in the form of solutions. Solutions are evenly mixed and completely dissolved. So a solute, don't confuse a solute and a solvent, by the way. Those are going to come up throughout the rest of your science career. A solute is what's being dissolved, and a solvent is what's doing the actual dissolving. So think about Kool-Aid. The powder is the solute, the water is the solvent. Water is actually a huge solvent for the body too. So you've heard about electrolytes in the body. Electrolytes are salts that are dissolved in water. We also have emulsions that are not evenly mixed but don't settle. So think mayonnaise. And then we have suspensions that are unevenly mixed, but they do settle out. So in the body, a really good suspension, or what you can think of as a suspension, is blood. So blood is a great example because if you put it in a centrifuge and you spin it out really, really fast, you can actually see the layers separating out. You can see the blood plasma separating out, everything else. We talk more about blood in anatomy too. Okay, chemical bonding. So elements have to combine with other elements to be stable, and that's where chemical bonding comes into place. If an element picks up an extra electron to be stable, it becomes more negative. So now we have an anion. So think about it as gaining a negative. If you're already negative and you're gaining another negative, then you're becoming more negative, right? So that's an anion. Conversely, so let's go back to that same element. If that same element instead gives away an electron to be more positive, so now it's less negative, then we have a cation. So ionic bonding strives for stability. Cations give away an electron to be stable, so cations become more positive because they're getting rid of a negative. And then anions gain an electron to become more stable, so they're getting another negative and they're becoming more negative. Anions are more negative, cations are more positive. In covalent bonding, we share electrons. We see more ionic bonding in the body than we actually see covalent bonding. And then hydrogen bonds overall are pretty weak bonds. It's an attraction of hydrogen atoms that creates that bond, right? The hydrogen atoms are attracted to each other, and that's what creates surface tension. We see a lot of hydrogen bonds in the lungs, and we actually see hydrogen bonds in DNA. H bonds actually hold the bases together in DNA, which we'll talk more about in another lecture. And then a quick touch on factors that actually can affect chemical reactions. Hotter temperatures cause faster chemical reactions. Higher concentrations. Concentration is the amount of solute. When there's more, when the concentration is higher, more solute, that can actually cause faster reactions. Small particles can increase the rate of reactions. And then we also have something called a catalyst. So catalysts are enzymes that speed up reactions. And we will talk about those in a later lecture. Surface area versus particle size. So let's read through this real fast. When a particle of a given volume is broken into two parts, like you can see in that picture, the total volume does not change. The surface area does change though. It increases by the amount of the two newly exposed edges. So what does that mean? So let's say we have this big block of salt at the top. Right? So we have this big, let's say, block of salt. We have all of these sides. So think of these sides as the only spots that water can attach to dissolve this big block of salt. If you take this big block of salt and you break it in two, boom and boom, then we have the same volume, right? Because all we did was break it in two. But we have more surface area because we just created two more sides right here to count more surfaces. So more surfaces equals more surface area, but the volume stays the same. So this small particle by itself has less surface area than the large particle, right? But if we're comparing the same volume, so both of these pieces to the same volume up here, both of these pieces have greater surface area because they have more sides than this big piece. Does that make sense? So the same volume to the giant piece, but the small pieces in total have more surface area. So if we just talked about a single piece, yeah, there's less volume, less surface area than this big piece. But when we're talking about the same volume in these two pieces, then the surface area in these two pieces is greater than the surface area in this piece. All right, so salts break down into positive and negative ions that we call electrolytes, and they help conduct electricity throughout the body. The common ones are sodium chloride, NaCl, CaCO3 is calcium carbonate, KCl is potassium chloride, and then lastly we have calcium phosphate. A lot of these can be found in the blood, and a lot of them can be found in the bone as well. Acids and bases, nothing new here. Some examples in the body of acids are different gastric juices, different hydrochloric acids, both in the stomach. And then bases, you see base or you see alkaline, that's the same thing. A common base in the body is actually blood. And then 7 is neutral, so think water is 7. Blood is actually 7.4, so it does make it slightly basic or slightly alkaline. Either way you say it, it's correct. When we talk acids, we're talking a pH of 0 up to 7, and then when we talk alkaline, we're talking pH of 7 to 14. Neutralization is when an acid or base is canceled out or neutralized. Back to 7 or back closer to 7 than what it was. Think high stomach acid. We need to neutralize it. So what do we have to do? We have to introduce a base, right? Or an alkaline solution to neutralize that stomach acid so that we're not having something like explosive diarrhea, right? Buffers, they help keep the body from going too far out of a normal range of whatever pH level you're in. And then the last slide here is of just a pH scale with some common items. You can see hydrochloric acids down here with a pH of 0. And you can see sodium hydroxide is up here with a pH of 14. In the middle, you have something that you're used to, household bleach. So pH 9.5, you know it's slightly basic. Egg whites are slightly basic at a pH of 8. Blood is slightly basic at a pH of 7.4. We got milk, which the body actually makes as well. Well, not everyone's, right? Black coffee, slightly acidic. We've got wine, slightly acidic. Well, pretty acidic here, 2.5 to 3.5. Lemon juice, pH of 2, very acidic. And then hydrochloric acid. So if you ever get confused, try and remember this scale, and then you'll remember. If you're closer to 0, you're more acidic. Closer to 14, more basic or alkaline. And that is it for our lecture over chemistry. It's not a very long one. Thank you.